we now look at the response of the system to U2. For that, I open a new window and I do the same thing as I did before, except now that I plot U2 in that window, followed by Z2. Again, I can look at the response on that window here. And what I see is that my U2 is now the sinusoidal component of e to the jt. Oops. Let me try it. So my U2 is the sinusoidal input component of e to the jt. And this system, this response is the response of the dynamical system, 1 over s squared plus 2s plus 1. And again, what you see is that I really would like to change this picture. There we go. It has a slightly transient component, and then it settles. It settles to this element, which is the imaginary part of this guy times e to the j omega t. So in this case of our example, it is e to the j times t. And therefore, we have that this is indeed true. Okay? Which is that the steady state component of the response is simply for a sinusoidal input, possibly decomposed or recomposed as a complex exponential. The response is equal to the evaluation of the transfer function at the frequency j omega, at the frequency omega of interest, times e to the j omega t. Now this has several interesting possibilities in terms of designing useful systems. When we know that the response of our system can be, or the excitation to our system can either be a sinusoidal input or a combination of these sinusoidal inputs at several frequencies. Okay. Thus, the computation of h of j omega is paramount to system dynamics. For example, we have several cases, mechanical cases, where the excitation of the system is periodic. One of them could be, and is covered in the book, as system with imbalance. What is a system with an imbalance? Well, it is a system which could look like this. Okay, it would be a non or an unbalanced wheel, the one you use for your cars. How do we model this? Well, a wheel is sort of a disk. The disk will assume uniform, okay, or we will assume it has a certain moment of inertia. The imbalance is equivalent to having a small mass located on the rim of the wheel, such that the mass of the wheel, which is called m, and the mass of the small element satisfy small m much smaller than big M. Okay. Now, what happens when we have this kind of behavior? Well, you have probably all driven a car which has an unbalanced wheel. The car has a suspension system which is made of a spring and a dashpot connected via some appropriate mechanism precisely to the center of the wheel. As the unbalanced wheel moves up and down along the highway, it transmits this vibration to the car, which also then moves up and down. As the speed goes up, the frequency of rotation of the wheel goes up, and the excitation frequency goes up, and the car oscillates at a different frequency as well. Not only that, but a different amplitude. And so it is of great value to understand the whole schematic. Now, we can start with a simple example. The simple example would be that the car is mounted upside down, lying on the ground, in such a way that the mass of the wheel is m, its radius is r. We assume the little mass causing the imbalance is on the edge, has small mass m, and the whole thing is mounted on a spring and dashpot system in such a way that the wheel can only move up and down. Okay, so you can look at it as a test bench. We assume the stiffness of the spring is K and the constant of the dashpot is mu. We write the equations of motion of the whole system. For the purpose of this exercise, we assume G is equal to 0, which is very much the same as the approximations or the simplifications we have done in the previous cases. We can easily derive from G is equal to 0 the case where G is not equal to 0, because it just creates a bias. Okay, so M goes up and down, M, the wheel rotates, and again, we need to write the various versions of Newton's law.